Welcome back, students. In this video, we're going to look at nucleophiles and electrophiles. We're about to get into starting looking at reactions in organic chemistry, and when you look at reactions, you're going to need to be able to identify the different kinds of compounds in reactions, and a lot of the time, the reactions are going to involve nucleophiles and electrophiles. Now, phile is the Latin root for love, so a nucleophile is something that loves a nucleus, and electrophile is something that loves electrons. I think it's easier for students to start in the context of electrophiles, so let's start with that. Electrophiles love electrons because they don't have them. See how this has a positive charge here? Well, it's lacking electrons, and thus it wants them. Well, let's look at nucleophiles then. If we look at nucleophiles love a nuclei, and you think because it lacks a nuclei? No, what it's happening is it has an excess of electron density, and so it wants the protons in another atom's nucleus. And so that's why I think it's a little bit easier to understand electrophiles and then work on nucleophiles. Let's look at these in more detail. When we look at nucleophiles, these are going to have electron density that it is able to donate. So there's going to be excess electron density in your nucleophiles. Here are two examples. This one has 3 lone pairs around the oxygen, and notice that this particular oxygen has a negative formal charge. If we just take that and we add a hydrogen, we still have a nucleophile here with that oxygen because there's an excess of electron density, but it's not a negative nucleophile. And when you start looking at nucleophilic strength, so which nucleophile is stronger than another one, you're going to recognize that negative nucleophiles are stronger than neutral nucleophiles. And that makes sense, right? Because if a nucleophile is something that loves a nucleus, it loves a nucleus because it wants the protons in some other atom's nucleus. It wants to be close to those. Well, if it has a lot of electron density, then it really wants to be close to the protons in another atom's nucleus. So things that have the excess electron density, meaning a negative charge, are going to be stronger nucleophiles and desire, if atoms and molecules had feelings, they're going to desire a nucleus more strongly. Don't fall into the assumption that lone pairs are the only way that you can experience a nucleophile. An excess of electron density can also show up as a pi bond, so pi bonds can behave as nucleophiles. Here on the left, I drew an example of a pi bond, and this pi bond, when we demonstrate how it's behaving as a nucleophile, remember that there are p orbitals on these carbons, and I didn't draw out the whole structure, I just kind of focused in on where my pi bond is going to be. And those p orbitals are sharing electron density above and below the node. The little yellow lines are meant to say that these are sharing electron density. And the squiggly lobes are my p orbitals. And so those p orbitals are sharing excess electron density, and that is also going to behave as a nucleophile. So what we're seeing is atoms that have excess electron density, like lone pairs, are nucleophiles. If that atom has a negative charge, that's even more nucleophilic. And that also pi bonds are an area of excess electron density and can behave as nucleophiles. When we start ranking nucleophilic strength, we consider something called polarizability. Polarizability is hard to imagine. I have the definition written out here, but I want to give you more of a real-life example to help you visualize it a little bit better. When I think about polarizability, I think about iodide ion being a slightly deflated beach ball. If I think about iodide ion as being a slightly deflated beach ball, or even one of those exercise balls that you use at the gym to do sit-ups on, you lay on it and you're like, crap, this thing's deflated. That's iodide ion, right? And what's happening is you, the external influence, are pushing on that ball and you're changing its shape. Whereas if you think of something like fluoride ion, Fluoride ion would be a ball that is much smaller and has less ability for something to influence its shape. So think of fluoride ion as being like a very small tennis ball. Maybe the size of the tennis ball isn't quite right to describe fluoride, but the fact that you can push on it a little bit, right? It doesn't give a whole lot. You can't really influence fluoride ion's shape. It can't really go out of the spherical shape very much due to an external factor because it's really holding on to its electrons. And when I was in advanced inorganic chemistry, I remember my professor talking about polarizability, and it made zero sense to me. And I remember going to her office hours, and she was just like, Caitlin, big and squishy and small and hard. And I was like, what does that even mean? And here what she was trying to explain to me is atoms or ions that are large are like beach balls that are partially deflated. They're squishy. You can change their shape with an external factor. That's called polarizability, when you can change their shape. Whereas things like fluoride have a small radius and thus are hard and difficult to manipulate their electron density. And the key is that the more polarizable the atom or ion, the stronger the nucleophile. So that means that you need to remember what the trends are for general chemistry for size when you're looking across and also up and down on the periodic table. Now, I know you know the up and down. I know that you know going down the column on the periodic table makes for a larger atom or ion, but I'm not sure if you remember that as you go left to right across the periodic table, that things get smaller, right? So if we're looking at our periodic table and we're going this direction, fluoride is actually smaller than nitrogen, which is smaller than oxygen, which is smaller than carbon. That's counterintuitive. If you're, forgetting about Z effective. So go ahead and maybe look that one up one more time if you need a reminder on why you're seeing the trends for ion or atom size that you are. The key here is the bigger the atom or ion, the more polarizable, which means it's a stronger nucleophile. Now let's transition to electrophiles. When we're looking at electrophiles, electrophiles are compounds that love electrons because they lack them. Right? Think about this with respect to money or candy or whatever you want to think about. We as humans want what we don't have. And if I am lacking in candy or cupcakes or dollars, I really want those things. And that's what your electrophile is like. Your electrophile is deficient in electrons and thus really wants them. There are a couple of examples of electrophiles. One is when you have an empty p orbital. If we look at the example over here on the left, this is a carbocation. That carbon has an empty p orbital. If you just look off to the side over here, I'm going to try to draw that empty p orbital. I accidentally covered up that bond, so I'm going to draw that bond over here so you can see it better. Remember that empty p orbital has a lack of electrons. It's like a hole. There's missing electrons there. And it's not just carbons that can have empty p orbitals. There's other atoms that can have empty p orbitals. It's just that we see carbocations as a really great example of an electrophile. Another type of electrophile is when you have a polar bond in a molecule. If you have a polar bond in a molecule, for example, here you have a chlorine, and chlorine is one of the more electronegative elements, and it's going to pull electron density away from the carbon, and I'm going to highlight the carbon that it's pulling electron density away from. That carbon is now going to be electron deficient. And because that carbon is electron deficient, that makes that carbon an electrophilic center. Right? The chlorine itself has lone pairs, and so those lone pairs could behave as a nucleophile, but the fact that the chlorine is pulling electron density away from the carbon is making the carbon an electrophile. Your electronegative atoms are going to do this. They're going to pull electron density away from carbon, leaving a partial positive in its wake, and that is going to be an electrophilic site. Here I have an example that I'd like you to do. I'd like you to go through and label as electrophile or nucleophile for these compounds, keeping in mind that in some instances you might end up calling one location of the molecule an electrophile and one location a nucleophile. So when you're ready, let's compare. It's time to compare, and I already wrote out the answers to 3 of these because these 3 are the ones that I think that you could get pretty quickly. The first one on the left where you have a pi bond, pi bonds are always nucleophiles. The one below it, you have a positive charge, well, you have an electrophile then. And then on the upper right, that sulfur has an excess of electron density. That sulfur is definitely a nucleophile. Then the other ones were a little bit trickier, so I wanted to talk about them more thoroughly. Let's go down the first column and see fluorine. Fluorine is your most electronegative element on the periodic table. What fluorine does is it pulls electron density its direction, and when it does so, it leaves a partial positive on the carbon that I'm highlighting. So that carbon is definitely going to be an electrophilic center. You could also say that the fluoride itself, the fluorine with its lone pairs, could act as a nucleophile. And yeah, I mean, that's true. But most of the time, what's going to happen in the reactions that we're going to see is the carbon structure, when there's a lack of electrons on that carbon structure, we're going to call that structure an electrophile. But if you have a teacher who wants you to label all the electrophilic or nucleophilic sites, so all the locations on an individual molecule that could behave as an electrophile or a nucleophile, then what you would do is you'd call the carbon an electrophile or an electrophilic site, and then the fluorine would be a nucleophilic site. Now let's look at the lithium example. For lithium, lithium is actually less electronegative than carbon, and what happens when lithium's less electronegative than carbon is the opposite arrow that you're used to drawing. Usually you're used to having the carbon have the partial positive charge, but that's not the case here. The lithium is the one that has the partial positive. So where I'm going to highlight in blue, that's actually a carbon with excess electron density. It has a partial negative instead of your typical, which is a partial positive. You're not going to see a lot of molecules like this. There's only a couple of examples in the future where you will see a metal bound to a carbon, and there's 3, and they're mostly in organic chemistry too, depending upon when you talk about them. But this one, the carbon right here, is definitely a nucleophile. If you wanted to get really particular, I guess you could call the lithium an electrophile because it does have a partial positive. But honestly, when we're in organic chemistry, a lot of times we don't care about metals. So they just go into the water system of your reactions and then we get rid of them. But if you wanted to be really particular, you could call that an electrophilic site. And then our last one is BH3. This one is tricky because it might be hard for you to see that there is an unused p orbital here. That boron is sp2 hybridized, and because that boron is sp2 hybridized, there is an unutilized p orbital which is empty. And because there's an empty p orbital, that is what makes this an electrophile. Let's wrap up. In this video, we looked at the definition of nucleophile and also electrophiles. We talked about how nucleophiles have electrons to share and thus want a nucleus. Electrophiles lack electrons and therefore want electrons. We also looked at comparing the strength of different nucleophiles, stating that negative nucleophiles are stronger than neutral nucleophiles, and we talked about polarizability. Make sure you can identify which compounds are nucleophiles and electrophiles. Thanks so much for your attention. This is Katoni signing out.